Well, let's look at how this 1s orbital combination would be shown on paper. So let's say we've got two 1s orbitals and we're going to assign them the same phase. We'll put positive and positive here. If we combine them together, we'll have a positive and a positive 1s, and we combine them and we get this sigma 1s, and that's a bonding orbital. And you can see that everything is all in the same molecular orbital down here. That's what's happening at this point here. The other possibility is to take a positive 1s and a negative phased 1s, and we try and combine them together. And when we do that, we end up with an anti-bonding situation. You don't see any bond occurring at all between unlike phases when we're talking about 1s orbitals. So that's how we get the sigma 1s star anti-bonding orbital. So this is a designation is sigma 1s bonding, and this one is sigma 1s star, and that's anti-bonding. Now when we get to p orbitals, things become a little bit more complicated. With p orbitals, remember, there are three possibilities. You've got one set of p orbitals along each axis, the x, y, and z, as I've designated them here. Let's first of all discuss what kind of orbitals can combine. Now, the only kinds of orbitals that can combine are the ones that will allow for overlapping orbitals. So what I'm saying here is that a px can combine with a px, a py can combine with a py, and a pz can combine with a pz, because we can get these orbitals to overlap because they're in the same area of space. What we can't do is we can't get a py to combine with a pz. That's because the orbitals for the py lie along the y-axis while these lie along the z-axis, and if you try and put them together, they will never overlap. So only like orbitals will have any chance of overlapping to begin with. So first of all, let's talk about what happens if we combine the two orbitals that I've designated px's. So this would be down here. Alright, so what we're looking at are the two px orbitals combining together. Let me show you again on the diagram so you can see what I'm talking about. We're taking this orbital and this orbital, we're combining them together, and this will create a bonding orbital. And you can see there's the bonding orbital right there. So this would be like minus, plus, plus, minus, and we combine them together. The two pluses can combine, and we get our nice bonding orbital. Looks kind of similar to the sigma bond we got from the combination of the two 1s orbitals. Now if we go ahead and we change this now and look at the anti-bonding situation, this would be where we've got unlike phases here. This would be like plus, and this would be like minus. So this would be minus, plus, minus, plus. And when we try and combine those together, because the phases don't have the same sign, they won't combine, and we'll get an anti-bonding situation. Going back to our diagram, you can see that that's the situation we're going to have here. So this would be the combination of the two px orbitals that I've got here. I'm calling that sigma 2px, and this up here would be called sigma star 2px. And what I'm trying to denote there is that this is bonding and this would be anti-bonding. And you can see that that's because we're using a different phase here, or trying to combine different phases. Alright, let's take a look at the other combinations, my py and my pz combinations. And what we're going to see here is when these combine, they're going to form a different kind of bond. Now look at the px's, you can see that this is going to be an end-to-end type combination. This here is going to be a side-by-side combination, and this one here is going to be a side-by-side combination as well. Let me show you what I mean by looking at the pz's. Now in this diagram they're designated as something else, but just pretend that these are the pz ones that I'm talking about. And this is what we're looking at. This is called a pi bond. So this is a side-by-side interaction now, where we're getting the top and the bottoms to both interact, and this forms one single bond where the electron density lies above and below the plane of the bond. That's what we're looking at. So let me go back to the orbital diagram. You can see what I'm talking about. Here's the PZ and here's the other PZ, and when they combine together, this is what we get. We get a bonding orbital between these two PZs that lies in between the z-axes, both above and below the plane of the bond. Let's take a look at what the anti-bonding situation looks like for that one, and that's this one here. And you can see that that's because we're using unlike phases, and when we try and combine them we get the anti-bonding pi orbital. Alright, so let's see what the designations would look like for that. This one here would be called pi 2pz, and this one here would be called pi star 2pz. So this one is from the combination of like phases, and this one is from the combination of unlike phases. Alright, let's take a look at the last one now. And you can see this will be my Y, and it's difficult to see, but the red is behind here, and we're looking at this from the side. So this would be the combinations of blues, and behind it you've got the combinations of the reds. So we're getting the same kind of bonds, it's just difficult to tell because we're looking at it straight on. You can see here as well that this would be the blues, and behind it would be the combination of the reds. So it's let's take a look at the anti-bonding on this one. It's a little bit easier to see, and again you can see that you've got the blues trying to combine with the reds and they can't, the red trying to combine with the blue and it can't. So we don't get a pi bond out of this, we just get an anti-bonding type situation out of that one. Alright, so on paper it looks like this. You've got the pi bond between the two y axes, and you've got the minus phase joined up here and the plus phases joined down here. So that would be from combination of this plus phase with this plus phase and this minus phase with this minus phase. And then when we try and combine them oppositely, we get the anti-bonding type situation over here. Alright, so the designation for that would be pi 2py for the bonding, and pi 2py, and that's star for the anti-bonding. Alright, so we've got all the bondings down the bottom, they're of lower energy, and then you've got all the anti-bondings, and they're of higher energy. So the bondings are all about like phases joining together, and the anti-bondings are all about the unlike phases joining together. If you want better pictures of those diagrams, you can see them in the PowerPoint notes, and I'm going to go and show you those. And here again is our combinations, and this is the s orbitals bonding together, and you can see like phases would form the nice sigma bond, and the unlike phases would form the anti-bonding situation, plus and minus over here. Here is our 2pz bonding, where we get the like phases, the pluses and the pluses, and we get that nice situation where the pluses combine and we get the pi bond. This is the pi z bond. This is the anti-bonding pi z bond, where we have the unlike phases. Here is our py and our py like phases. We get our nice pi y bond here, and here's the pi star y antibond that results from the opposite phases. And here is the px sigma bond, and we get this from an end-to-end type arrangement of the orbitals rather than a side-by-side one, and we end up getting our sigma orbital here from the like phases and our anti-bonding orbital from the unlike phases. So I'm hoping that you can see the difference between these two. You've got the pi bond here and here, and the sigma bond here. The pi bond results from side-by-side arrangements like this one and this one, whereas the other one results from an end-to-end arrangement.